Okay, so assignments for this week, I've got homework 3 and homework 4 that are due Wednesday and Thursday. Those should help prepare you for Friday's quiz. So remember, we're looking at chapter 1 and chapter 2. Now, the last section of chapter 2 is naming compounds. I might put ionic compounds on there. I will not put covalent compounds on there. So they have different sets of naming rules. So are there any questions about things that are coming up? So hopefully you've already done homework 2. That's an active chemistry, yeah. So I will try to put active next to things, and everything in active chemistry should be labeled with HW for homework. So if you ever see that and I haven't written the word active, you should be thinking of active chemistry. Okay, so you have out the packets that we started in class on Friday, and were there any questions that you had trouble with, or you weren't sure of the results you wanted to ask about? All right, this all seems like this works well for you. All right, excellent. So I'll come around and pick those up. So sometimes I will ask a question where I will give you sort of generic looking isotopes. Oh, I should say I'm wearing a mask today because I have a cold. I don't have COVID, I promise. But I have a cold, so I don't want to share it with you. When I'm back here and away from you, I think I might take the mask off because it is really hot and in here. But if I'm moving around the room close to you, I'll try to put it on. This way, hopefully you can understand me a little bit better. Anyway, so if I give you a generic symbol like this, can you tell me what that element is? What do you think? Nitrogen. And how do you know that? The 7. So remember, this number here is going to tell you what that is. And so if you have an X here or some letter that's not an element, that's indicating I'm trying to disguise what the element is and see if you can figure it out. So sometimes I'll put several of them together. So I might do something like, let's do, okay, so I've got a bunch of symbols here. None of these are actual element symbols. So which 2 of these could be the same element or should be the same element? And you answered the last time, so I'm not going to let you answer this time. We'll go to the other side of the room, Tristan. X and E. And so we know that again by looking here. Okay, so sometimes it's really tricky because we've got 3 of these that have the 40 at the top. They have the same mass number, but they don't have the same number of protons. And it is the protons that tell us what the element is. Okay, so just kind of keep those things in mind when you see a test question. They won't all be like, put this together the way the back of the chart was. Okay, so the paper that I handed to you was one that I had intended on having when we were talking about the periodic table, and I forgot to print it out for class. So I'm just going to remind ourselves of some of the things that are on the periodic table. So the point of this is you don't really need to know the specific elements. You will always have these periodic tables that have the names and the element symbols on them. So you don't need to memorize those. But what you do need to know are some of the names and the common trends. And so we talked about some of the groups here. So what was true, there were a couple of things we learned about this column. The first column we call the group or family. So first of all, what was the family name? That should have been in your notes, Tristan. Alkali metals. All right. And what was the charge? What was it? Close. Nope. The one was right, but Positive, positive one. So this side is all positive. Okay, and then this one was +2. All right. This had a very similar name, alkaline earth. Metals. And I can't remember, I don't think we named this group in the middle, but most of you know this is a group called the transition metals. So notice metals, metals, all of this is metals. I can't remember if in this class we talked about these bottom two. We don't do too much with them. These are the lanthanoids. Your book calls them the lanthanides. That term was used for a long time, but as we will discover as we are naming compounds, the ending "ide" really means negative, and these don't form negatives. So these are the lanthanoids and the actinoids. And they actually fit inside the periodic table. So you see the purple and the pink here at the bottom. This whole couple of rows here fit right in that spot. So we had them in the periodic table. The periodic table is super, super long. So they're taken out just for convenience of looking at the table, not having a super long table, but that's where they belong. So these are sometimes called the inner transition elements, or inner transition metals. All right, and then we talked about columns on this side. So what do we know about this very last column, column 18?
They're very stable.
They're very stable, and since they're so stable, they don't tend to gain or lose electrons, and so their common charge is 0. And we have lots of names for them, but the one that makes the most sense is the noble gases. They're sometimes called the rare gases, but they're not very rare. They're sometimes called the inert gases because they're not very reactive, but we actually can form compounds with them, so they're not completely inert. All right, so what's the charge on this column that's right next to the noble gases? -1. Okay, so going from the outside in, they get bigger and bigger numbers. It's from the right, they're more negative, and from the left, they're more positive. So then this one would be -2. You should know the name halogens. That term is used quite a bit. I probably won't say, what's the name of column 17, but I may in class talk about, this is a halogen. We should be looking at the halogens. And so I want you to recognize that column as being the halogens. This term, you'll see it's in your book, but it's not used very often. So just because we have names for the other columns, I'm putting it there, but you don't really need to know it. It's called the halogens. Okay, did we talk about the diagonal line? I can't remember. No, okay. So you'll notice on this periodic table, there's kind of this round diagonal area. And then on this older one, if you have really good vision, you can see there's a dark blue zigzagged line. Okay, so this line has a name that you don't need to know. It's called the central border. And all of the elements that sit on top of the line are what we call metalloids or semi-metals. All right, so those elements have properties that are kind of in between. Technically, the difference between them is that they have more than one allotrope. So remember, allotropes are forms of the element. And one of the allotropes behaves kind of like a metal, and another allotrope behaves kind of like a non-metal. You don't need to know that, but that's what makes that distinction. We won't work too much with the semi-metals because I don't want to end up in this territory where it's like, well, do we treat it like a metal? Do we treat it like a non-metal? Most of the time we will treat them like non-metals. But I will try to avoid using that area to avoid confusion. So all of the elements that sit on top, and then there are two that sit right below, germanium, and antimony. Okay. So the reason that I point this out is that most of the periodic table, including these down here, are metals, right? And metals are very conductive. So if I take my if I go in the other direction, my least conductive metal, and they're conductive in 3 directions, all 3 dimensions, every which way, and compare it to my most conductive non-metal, there's about 1,000 to 10,000 orders of magnitude of difference in the conductivity. So there's a really stark difference between them. Metals will form cations, and what are cations? Positive charges. Okay, and so that's why it's important to know that this is +1 and not -1. We're going to be naming compounds and we're going to put the cation first. So we need to know which one's going to be positive. So all of this stuff is going to be positive. We're not going to use lanthanoids or actinoids, but if we did, they would be positive. And just this corner up here is going to be the nonmetals. And since the noble gases aren't really going to be part of the compounds we're looking at, we just have, you know, maybe a dozen elements over here that will form anions. So the nonmetals form anions. Okay, so throughout the semester, for various reasons, we're going to need to know the difference between a metal and a non-metal. And I'll keep coming back to look at the diagonal line on the periodic table. Which side of that line does our element fall on? And that's going to tell us the difference between the metal and the non-metal. So hopefully over the weekend, you looked a little bit at forming formulas, the different kinds of formulas. We talked about this a little bit in class. And we're going to see that depending on whether we have nonmetals or metals, we're going to get different kinds of compounds. And those different kinds of compounds, we might look at their formulas a little bit different. So first thing we need to talk about is bonding. There are 3 basic types of bonding. As you get into higher levels of chemistry, there are variations on these that become some subcategories. But 3 basic kinds that we think about, and one of them that we completely ignore. So really it's just 2. So the first kind is covalent bonding. And so the key here is that we are sharing electrons. Every bond involves 2 electrons, and those 2 electrons are shared between 2 atoms. And again, as you get in higher levels of chemistry, there are some exceptions and variations on this, but for simplified purposes, this is where this happens. This is almost always between nonmetals. And sometimes our semi-metals will participate in this. 2 electrons. So E with a minus is how I will abbreviate electrons. Thank you for asking that. All right, so these types of things, because they're sharing these electrons, they end up with a stopping point where like all of the sharing is on the inside, and so there's nothing attached to the outside. And so they form molecules. And so when we talked about Dalton, we kind of talked as if everything forms molecules, but that's not actually true. Sometimes we form crystals, and crystals are extended structures where we just kind of keep repeating the pattern over and over and over again. So our ionic bonding is where we see that. So this is where we have oppositely charged ions, the cation and the anion, and they are attracted together electrostatically. So electrostatically just means that opposites attract, that we have a negative and we have a positive, and that's the attraction. Sometimes we'll use the term electrostatic to mean that like charges will repel, but most of the time we're dealing with the attraction. So if I look at something like sodium chloride, this is a model of sodium chloride. Now, when we write the formula for sodium chloride, many of you know, we just call it NaCl, right? But there's not a molecule of NaCl. So this is our table salt. So you can see it forms just kind of a grid pattern. I call it a three-dimensional checkerboard because like the face looks like a checkerboard, but if I turn it this way, this also kind of looks like a checkerboard. And this pattern isn't even this small. It goes on ad infinitum in all directions until you have orders of magnitude, 10 to the 15th atoms in any tiny little crystal that you might have, okay? So since it does this, and each crystal might have a different number of atoms in them, depending on how big or small the crystal is, we don't actually talk about the formulas as if it is one molecule. We just give the lowest ratio of the compounds. So because we have this alternating green, gray, green, gray, green, gray, sodium, chlorine, sodium, chlorine, sodium, chlorine, we know the ratio is 1 to 1. And so when we write the formula, we just write NaCl. So these form, sometimes we call them extended structures. And that's going to include a few things we won't talk about in this class, like nanotubes. But mostly we're thinking of crystals. Key thing is here, they don't form molecules. Okay, so since they don't form molecules, we just look at the lowest ratio of the atoms. All right, so when we have only metals, so if we had pure sodium or if we have pure gold or pure aluminum, the reason why the atoms actually stay together in a lump of gold or whatever is that they are sharing electrons, but they're not sharing them just between two atoms. I like to say metals are communists. They just like, everybody gets everybody's electrons. And so the electrons can move all over the place, and this is why we have conductivity. So if you think about going to a swimming pool, you might be the nucleus of an atom. You don't say, this is my water molecule. I don't want you to play with it. You play with your water molecule. Or the two of us are sharing this water molecule. You can't have it. Everybody uses all the water, right? And so sometimes people will say that the electrons in a metal are like that water. They say it is a sea of electrons. Now, metals, because they are pure elements, a lot of times we just don't deal with them a whole lot. We just name them as the element. So we're not going to deal with this metallic bonding too much. It'll come up a couple of times throughout the semester, but mostly we're going to focus on these other two kinds of bonding. Okay? All right. So we looked a little bit at formulas last week. I think it was the beginning of last week, where we said we could have the formula that described what the molecule looked like, or we could have a formula called a condensed structural formula that kind of shows the shape of the molecule. We have a couple of different kinds of molecules, and they depend on whether we're looking at actual molecules or extended structures. So one is called the molecular formula, and we can only use it for covalent compounds. So it's going to show how many atoms of each element that we would have in a molecule. So this is one of our smaller molecules called ammonia. It's got a nitrogen and 3 hydrogens. So I could draw a picture of it in our particulate domain, or I might have a model of this, but I would write the formula in the symbolic domain as NH3. And I'll say this throughout the semester, we don't tend to write ones in chemistry. Ones are invisible. So there's kind of an invisible one next to this nitrogen, but we don't write it, okay? So if I have something like sodium chloride, I'm not writing what's called the molecular formula because there are no molecules. What's important is that even if I have a big molecule, I would be showing all of the element or all of the atoms that are in there. And sometimes that can be, if you're talking about a protein, you know, those are thousands and thousands of atoms. So those can be quite complicated formulas. As we mentioned, we might also have a condensed structural formula. And this is a kind of molecular formula. So the condensed structural formula, it's still showing all of the atoms and all of the elements. It's just not grouping them together. So we're not putting all of the hydrogens together because it's trying to show us a little bit about the structure. The most common place to see this is with organic compounds. Organic compounds tend to have carbon. Okay, so I might write a formula like this. I could just write the normal molecular formula by saying, okay, there are 4 carbons, so C4, and then there are 2, 4, 6, 8 hydrogens, so C4H8O2. Okay, that could be one way I could write this. But by writing it in this way, I'm showing you there's a carbon with 3 hydrogens, then there's a carbon with 2 hydrogens, then there's a carbon with 2 hydrogens, and then there's a carbon with an oxygen, and then an oxygen and a hydrogen. So when you take organic chemistry, it's going to make a lot of sense to put things this way because you're going to be able to see all of those different groups and how they fit together. So you might be thinking, why in the world is this called condensed? Because this is like writing it out more than you would if you just grouped all the carbons together. It's condensed from writing out the full structure if I were to draw it like this. So it's condensed from drawing the structure. Okay, so our other kind of formulas that we usually deal with are empirical formulas. And so this is going to be our lowest ratio of our elements. And the most common place we see this is for our ionic compounds. They have to be in an empirical formula because there's just not one molecule. There's no way to do a molecular. I will show you when we get to naming compounds why this is the case, but sometimes we might do a little bit of splitting up of the elements because we're dealing with ions. So we're showing the ratio of the ions. If we have polyatomic ions, then sometimes 2 polyatomic ions might have the same element. We'll get back to that. So it's really good for these crystals, these extended structures. And so we generally put the metal and then the non-metal. Since in English we read from left to right, we're going from the stuff that appears on the left side of the periodic table, the metals, to the stuff that appears on the right side of the periodic table, the non-metals. So we tend to go in that direction. So this is usually true. What is always true is cation, then anion. So we have one cation, and I'll come back to this when we're naming. We have one cation that is made of non-metals, and that's why I say this is usually true. So ammonium, NH4 plus, is a cation because it has a positive charge, but ammonium, nitrogen, and hydrogen doesn't have any metals in it. So in that case, we'd be looking at cation and then anion. All right, so we use it for our ionic compounds, but we can use for big covalent compounds. So if I had the molecule for glucose, many of you know glucose is C6H12O6. The empirical formula is going to be reducing this to the lowest ratio. So just like with fractions, I'm going to look for the biggest number that I can divide into all of those. So all of those 6, 12, and 6 are divisible by 6. So I'm going to divide them all by 6. This is the molecular formula. The empirical formula is CH2O. Okay. So why might we do this? Sometimes if we have an unknown compound, we actually don't know what the molecule looks like, and it's easier to figure out what the ratio of the atoms are than to figure out which atoms are in a molecule. So there is a certain kind of analysis we'll talk about probably next week that we can figure out these ratios, but we wouldn't necessarily know how big the molecule was. So this is why it's called empirical. Empirical means testing. We can do a test to determine those ratios, and that's a lot easier and cheaper than figuring out what the individual molecules look like. All right. Questions about the difference between molecular formulas and empirical formulas? Okay, so now we're going to go on to naming. So hopefully you looked at that prepare to learn for naming. And I should have put that on the board too. You have your prepare to learn 2C that is due, I think, Tuesday night on the other kind of naming. But we'll focus on ionic today. This is in section 2.7. If you want to compare your class notes to what you were doing, let's tilt this so that see, so that you can compare your class notes to what you're reading in the book. And so nomenclature just means how we name compounds. So the first thing that I want to say is that we are going to use the systematic rules. And so when I ask you on a test or a quiz, that's what I want. So if you Google something and say, what's the name of this compound? Sometimes it will give you the original name when they knew a chemical, but they had no idea what the formula was. So they started calling it something, and it has nothing to do with the common naming rules. Sometimes you will hear the terms like ferric or cuprous and things like that. Those are older rules that we're not going to use. So we are going to use the standardized, internationally accepted ones because they're ones that give us the most information about the compound that we are looking at. All right, so the first thing that we need to know is what kind of compound we are naming. So there are 3 sets of rules that we will worry about. Okay, so we talked about the difference between ionic compounds and covalent compounds. So ionic compounds, these will have a metal and a non-metal. Okay, the only exception to that is if we see ammonium, doesn't happen to be a metal. If ammonium is in there, then we need to use these naming rules. If we have only non-metals, we're probably going to use the covalent naming rules, but there is a subclass of covalent compounds that are organic, and they, because carbon just has all kinds of ways it can combine, it has its own set of rules. So if we see a lot of carbon, those would be the rules we will look at. We're not going to worry about those naming rules right now. We will get to that probably later in the semester, and then next semester in lab, we will spend some time looking at organic naming rules. So for right now, our concern is really just these 2. All right, so the first thing that you need to do is to decide, if I am looking at the formula for a compound, which set of rules do I apply? So if I have something that is CaCl2, which set of rules am I going to use? What do you think? Ionic. And how do you know? And how do you know that calcium is a metal? So it is in this second column on the periodic table. So we know that's the alkaline earth metals, but also it is to the left of that diagonal line. So remember, I'm going to keep going back to that line. That tells us everything from that diagonal line over. That is a metal. If I see a metal, this is the only place metals occur. There are no metals in these 2. So if I see a metal, I'm using ionic naming rules. All right. So what if I have, let's say, this.
That'd be covalent.
That's going to be covalent. Okay. It doesn't have a metal, but it also doesn't have carbon. So I'm going to use my covalent rules. Okay. What about this? That one is also ionic. How do you know? It has lead. So Pb is lead. It appears on this side over here. So it's not all the way over to the left, but it is still left of that diagonal line. Okay, so that's going to be what divides it. Also, if you look at some of the elements that are in that area, you know lead is a metal. You know tin is a metal. You know aluminum is a metal. So, if you just think to yourself, oh, it's got aluminum in it, clearly that's a metal. That's how we would name it. Okay, so let's look at some of our rules. So we are going to name the cation first, and then we are going to name the anion. The cation has what kind of a charge? Positive. Remember, it has pause. The cat has pause. It is positive. All right. So our cation is the positive one. This is the one that is likely a metal. Our exception to that is NH4 plus. That is also a cation because it has a positive charge, and it happens to be on your sheet. It's not one I asked you to memorize, but this one is named ammonia. So most of the time when you see IUM, yum, most of the time that means that we're dealing with something that is metallic. And so this is named that way because it behaves like a metal. It behaves almost identically to sodium. Pretty much anything that ammonium does, sodium does. All right, our anions are a little bit more complicated. So for the metal, we just use the name. In group 1 and group 2, we always know the charge. It's always either +1 or +2, depending on which column it's in. So we just stop it. We don't have to give any more information. But if it is not in group 1, if it is group 3 through, let's see, polonium is over there in 16, in those, then we have to tell what the charge is because they can change. Okay. So we would have the name, and then we would have a Roman numeral. So I'm going to put RN for Roman numeral that tells us what the charge is. So I for 1, I for 2, I for 3. What's 4? IV. So +4 is IV. 4 plus 5 is B. That's usually as high as we go. Sometimes you'll have +6 or +7. Okay. So for the metal, we will add a Roman numeral unless it is in those first 2 columns. Now, chemistry's got to be weird. There are exceptions. I will kind of let you go either way in the exceptions, but in your homework, they're going to be picky about this. So also with group 1 and group 2, aluminum pretty much only forms a +3 charge. So we don't usually put a Roman numeral with aluminum. Now aluminum sits up here in group 13. We're going to form a diagonal line going backwards. The 3 elements I'm going to tell you about are right together. So zinc tends to form a +2, almost never does anything other than a +2. And silver almost never does anything other than a +1. So as I said, active chemistry is going to be picky about that. I will be less picky about that. So you should not put a Roman numeral for group 1 or 2. That I will be picky about. This one, I've seen it both ways, but systematically, you're not supposed to put the Roman. Okay, the anion. Get this off the screen here. So if it is monoatomic, we would change the ending of the element name to I. So sulfur becomes sulfide, oxygen becomes oxide, iodine becomes iodide. Then for polyatomic, we're just going to use the name of the anion. And so this is why I ask you to memorize the things that are on the sheet, because you're going to see NO3 in a lot of compounds in class and in lab. And so you need to know that that's nitrate. You're going to see SO4. You're going to see OH. And so we're going to name those according to those rules. All right, so I gave two examples and asked you if they were ionic or covalent. We said they were ionic. So we're going to name CaCl2. Which are we going to name first, the calcium or the chlorine? Calcium, because it is the metal. And fortunately, the names tend to go in the order that they are written. So we just go in this order. Do I need a Roman numeral for calcium? No, because it is in group 2. So it's just going to be +2. And then what am I going to do for chlorine? So we are going to, so this is a little bit confusing. So we say monoatomic ions, that just means one atom. Think of it more like one element, because technically each of these chlorines behaves as independent of one another. So if we don't see more than one nonmetal there, we're going to assume it's monoatomic. So we're actually going to call this chloride. Okay. Now the other one we had was PbNO3(2). So we know that it is what metal? Lead. And this is where we have to do a little bit of thinking. Lead can have a couple of different charges, and we have to figure out what that charge is. So in order to figure out the charge, we're going to go to the anion. So has anybody memorized the charge on nitrate yet? -1. Okay. And I have 2 of these. All right. So this is a -1 and a -1. So to balance that, what does the charge on the lead have to be? +2. So let's say lead 2. And then because this is a polyatomic ion, there's more than one element there. We're just going to use that anion name nitrate. Okay. Let's do one more example. We are going to look at TiO2. All right, so this is probably an element that if you haven't had chemistry before, you don't know off the top of your head. It is in the transition metals in the top row. So if you find a periodic table, what is it? Titanium. Titanium. All right. We're going to need a Roman numeral for it because it's in the transition metals, but we have to figure out what oxygen is doing first. So what's the charge of oxygen? -2, because it's in that group 16. There are 2 of them, so we have a total of -4 here. So what's the charge on the titanium? Okay, so this is going to be titanium Roman numeral 4, and then how do we name this? Oxide. We just changed the end. Okay, so notice that this number here is not the number in the formula. Okay, that is one of the most common mistakes. People want this to be the 2. It's not the 2. Okay, it is telling us what is the charge of the titanium. Okay. All right, so don't forget the prepare to learn also before Wednesday, and then homework for you is due Wednesday night, so you have a little bit of extra time to work on that. Have a good week.